Have you ever tried to walk on a super slippery, icy sidewalk? It's tough, right? You take tiny steps, your arms flail around, and you feel like you might fall at any moment. Now, think about walking on a dry, carpeted floor. It's easy. You don't even have to think about it. The reason for this huge difference is an invisible force that is all around us, all the time. That force is called friction. It's the force that pushes back when you try to slide something across a surface. Without it, our world would be an uncontrollably slippery place. Everything would just slide around forever. Friction is the secret ingredient that helps us walk, run, and even just sit still in a chair. Friction is happening everywhere, in nearly everything we do. When you rub your hands together to warm them up, that warmth is generated by friction. When a car's brakes squeal to a stop, that's the sound of friction hard at work, converting the car's motion into heat. Even writing with a pencil on paper relies on this force. The friction between the graphite and the paper scrapes off tiny particles that leave a mark. It's the reason a soccer ball eventually rolls to a stop on the grass, and why you can hold a glass of water without it slipping through your fingers. It's a force of resistance, a force that opposes motion, and it is absolutely essential for our daily lives to function the way they do. This force might seem simple, but it's actually a fascinating and complex part of physics. It's a contact force, which means it only happens when two objects are physically touching each other. You won't feel friction from something floating across the room. It's the interaction between the surfaces of those two objects that creates the resistance. Think of it as the universe's natural braking system. Every time something starts moving, friction is there, trying to slow it down and bring it to a stop. It's a constant battle between the force that wants to create motion and the friction that wants to prevent it. Understanding this push and pull is the first step to understanding how so many things in our world work. So, as we dive into the science of this incredible force, remember that it's not just some abstract idea in a textbook. Friction is a hands-on, real-world phenomenon that you experience every second of your life. From the way your shoes grip the floor to the way a meteor burns up in our atmosphere, friction is the silent, powerful force shaping our world. It can be a helpful friend, allowing us to build, move, and control things. It can also be a bit of a nuisance, wearing things out and making machines less efficient. But one thing is for sure, without friction, our world would be an unrecognizable, chaotic, and very, very slippery place. Now let's get into the nitty-gritty. It turns out that friction isn't just one single thing. It has two main personalities, or types. The first type is called static friction. The word static means not moving, and that's exactly what this kind of friction does. Static friction is the force that you have to overcome to get something to start moving in the first place. Imagine a heavy box sitting on the floor. If you give it a tiny, gentle push, it doesn't budge. Why? Because static friction is pushing back against you with an equal and opposite force, keeping the box perfectly still. It's like the box's personal bodyguard, preventing any unwanted movement. Static friction is a bit of a smart force too. If you push a little harder on that heavy box, the static friction pushes back a little harder to match you. It will keep increasing its resistance to match your push, but only up to a certain point. This maximum point is the limit of its strength. Once you push harder than that maximum static friction, you break its hold, and the box will lurch forward and start to slide. This is why it often takes a big initial effort to move heavy furniture, but once you get it going, it becomes a little easier to keep it sliding. That initial grunt and heave is you battling and winning against maximum static friction. Once the box is sliding, a different type of friction takes over. This is the second personality, and it's called kinetic friction. The word kinetic relates to motion, so this is the friction that acts on objects that are already moving. As you slide that box across the floor, kinetic friction is the force that is constantly trying to slow it down. Unlike its static cousin, kinetic friction is usually a bit weaker. This is the reason it feels easier to keep the box moving than it was to get it started. The surfaces are already sliding past each other, so the force of resistance isn't quite as strong. Kinetic friction is more consistent than static friction. While you're pushing the box at a steady speed, the kinetic friction force stays pretty much the same. It doesn't adjust its strength the way static friction does. It just provides a steady, constant drag on the moving object. Think about sledding down a snowy hill. As you slide down, Kinetic friction between your sled and the snow is what eventually brings you to a stop at the bottom of the hill. If there were no kinetic friction, you would just keep on sliding forever. So remember the two faces. Static friction keeps things still and kinetic friction slows things down once they're moving. So we know friction is a force that happens when surfaces touch, but what is actually going on at a microscopic level to cause this resistance? If you could zoom in on any surface, even one that looks perfectly smooth like a polished tabletop or a pane of glass, you would see that it's not smooth at all. It's actually a rugged landscape of microscopic hills and valleys. Scientists call these tiny bumps and pits asperities. When you place one object on top of another, like a book on a table, the surfaces don't actually touch everywhere. They only make contact at the very tips of these tiny, jagged peaks. It's like two mountain ranges crashing into each other. When you try to slide the book, these microscopic mountains get in each other's way. The little peaks on the bottom of the book crash into the peaks on the surface of the table. To get the book to move, you have to provide enough force to either push the bumps up and over each other, or, in some cases, to actually break them off. This process of deforming and breaking these tiny surface features is what creates a lot of the resistance we feel as friction. It's a physical, mechanical clashing on a scale so small we can't even see it. It's like trying to drag a giant rake across a gravel path. It's going to get snagged, but that's not the whole story. There's another, stickier force at play, especially on very clean and smooth surfaces. This force is called adhesion, which is caused by the tiny electrical attractions between the atoms and molecules of the two different surfaces. When the atoms on one surface get very, very close to the atoms on another surface, at the points where those asperities touch, they can form temporary weak bonds. It's like they're holding hands for a brief moment. For the surfaces to slide past each other, you have to apply enough force to constantly break these tiny bonds. This constant breaking and reforming of molecular handshakes adds to the overall force of friction. This combination of mechanical interlocking and molecular stickiness is the true source of friction. For rough surfaces like sandpaper on wood, the crashing of asperities is the main cause. For incredibly smooth surfaces like two polished blocks of metal in a vacuum, adhesion becomes much more important. In fact, if you make two pieces of the same metal perfectly flat and clean and press them together in space where there's no air or dirt, they can actually stick together permanently in a process called cold welding. It's all because those atoms get so close that they can't tell which piece of metal they belong to anymore, forming one solid piece. It's a powerful demonstration of the sticky side of friction. Now that we know what friction is, let's explore what makes it stronger or weaker. It's not just random. Physicists have figured out the main factors that control the amount of friction. One of the most important factors is the normal force. That's just a fancy term for the force that presses the two surfaces together. For an object sitting on a flat, horizontal surface, the normal force is simply the object's weight. The heavier the object, the greater the normal force, and the more the two surfaces are squished together. This increased squishing means those microscopic hills and valleys are pushed together more firmly, making it harder for them to slide past each other. Think about it this way. It's much easier to drag an empty backpack across the floor than a backpack filled with heavy textbooks. The shape and size of the backpack didn't change, but its weight did. By adding the books, you increased the normal force pressing the backpack against the floor. This, in turn, increased the force of friction you had to overcome to move it. So, a simple rule is that friction is directly proportional to the normal force. If you double the weight of an object, doubling the normal force, you will roughly double the force of friction. It's a straightforward relationship that we can see and feel all the time. Another factor people often think affects friction is the contact area, how much of the surface is touching. You might guess that a wider object would have more friction than a narrower one, but surprisingly, for most everyday solid objects, the contact area doesn't really matter. Imagine you have a brick. You can lay it flat, or you can stand it on its skinny side. In both cases, the force of friction you feel when you drag it is about the same. Why? When the brick is flat, its weight is spread out over a large area. When it's on its side, the same weight is concentrated on a small area. The pressure is higher, but the total force of friction remains the same because the real microscopic contact points adjust. Finally, the most important factor is the nature of the surfaces themselves. This is described by a number called the coefficient of friction, represented by the Greek letter mu. This number is a measure of how grippy or slippery two specific surfaces are when they interact. For example, the coefficient of friction between rubber and concrete is very high, grippy, while the coefficient between waxed skis and snow is very low, slippery. Scientists put all this together in a simple equation. F equals mu times N. This means the friction force equals the coefficient of friction multiplied by the normal force. This simple formula is a powerful tool for engineers who design everything from car brakes to artificial hip joints. So, while friction is incredibly useful, sometimes it's actually the enemy. In machines with moving parts like a car engine or the gears of a bicycle, friction creates unwanted heat and causes parts to wear down over time. It wastes energy and, honestly, makes machines less efficient. If you want your machine to run smoothly and last a long time, you really need to find ways to reduce friction. The most common way to do this is by using a lubricant. A lubricant is a substance, like oil or grease, that you put between two moving surfaces. It creates a thin, slippery film that keeps the surfaces from directly touching each other. Think back to those microscopic mountains, the Hesperides. When you add a layer of oil, it fills in all the tiny valleys and creates a smooth layer over the peaks. Now, instead of the solid surfaces grinding against each other, they're separated by a cushion of liquid. The parts just glide on the film of oil. This drastically reduces the resistance because, well, the friction within a liquid is much lower than the friction between two solids, and that's why you need to get the oil changed in a car. Over time, the oil gets dirty and breaks down, losing its ability to lubricate effectively. Without that protective film, the metal parts of the engine would grind together, creating immense heat and causing the engine to seize up. There are different types of lubricants for different jobs. For high-speed machinery like an engine, thin liquid oils are perfect because they can flow easily and carry away heat. For slower moving parts that need the lubricant to stay put, like the bearings in a skateboard wheel or a door hinge, we use grease. Grease is basically oil mixed with a thickener, like soap, to give it a semi-solid consistency. It clings to the parts and provides long-lasting lubrication without dripping away. Even water can be a lubricant, which is why a wet floor is so slippery. And in some special cases, we even use gases like air as a lubricant, which is how an air hockey table works. Besides adding lubricants, we can also reduce friction by choosing the right materials. Some materials are naturally very slippery. The most famous of these is a polymer called polytetrafluoroethylene, but you probably know it by its brand name, Teflon. Teflon has one of the lowest coefficients of friction of any solid material. Its molecules are structured in a way that they just don't like to stick to other things, creating an incredibly smooth and non-stick surface. This is why it's used to coat non-stick frying pans. The food slides right off. It's also used in industrial applications, like making bearings and seals that need to operate with very little friction and no messy oil. We've talked a lot about how to get rid of friction, but just imagine trying to live without it. You wouldn't be able to walk. When you take a step, you push backward on the ground with your foot. It's the force of static friction between the sole of your shoe and the ground that pushes you forward in response. Without that grip, your foot would just slip backward, and you'd be running in place, going nowhere, like a cartoon character on a banana peel. Every step you take, every time you run, every time you jump, you are relying completely on static friction to get you moving in the direction you want to go. The treads on the bottom of your sneakers are designed specifically to increase this friction. This need for grip is even more critical when it comes to vehicles like cars. A car's tires are one of its most important safety features, and their entire job is to create and maintain friction with the road. When a car accelerates, the engine makes the wheels turn. The static friction between the tire and the road is what grips the pavement and pushes the entire car forward. When you turn the steering wheel, it's static friction that allows the tires to push sideways on the road, changing the car's direction. If you tried to turn on a perfectly frictionless surface, the wheels would turn, but the car would just keep sliding straight ahead. Braking is perhaps the most life-or-death example of useful friction. When you press the brake pedal, brake pads clamp down on a disc connected to the wheel. The immense kinetic friction between the pads and the disc converts the car's energy of motion into heat, a lot of heat, and slows the wheels down. But that's only half the job. The final, crucial step is the friction between the tires and the road. This friction provides the stopping force that brings the car to a halt. This is why it takes much longer to stop on a wet or icy road. The water or ice acts as a lubricant, reducing the coefficient of friction and weakening the tire's grip. So, from the simple act of holding a pen to the complex engineering of a race car, friction is our friend. We use it to fasten things with nails and screws. Friction holds them in place. We use it to play musical instruments like the violin, where the friction of the bow against the string causes it to vibrate and make sound. Athletes wear special shoes with cleats to dig into the ground and maximize friction for quick starts and stops. In countless ways, we have learned to harness this force, designing surfaces and materials that provide just the right amount of grip to make our technologies work and keep us safe. Friction has a few tricks up its sleeve that might surprise you. One of the most amazing is a phenomenon called the capstan effect. A capstan is a large, rotating drum or post, historically used on sailing ships to pull up heavy anchors. The effect describes how friction can amplify a force exponentially when a rope or cable is wrapped around a cylindrical object. Imagine trying to hold back a very heavy weight that's tied to a rope. If you just hold the rope, it might be impossible to stop it from slipping through your hands. But if you wrap that same rope around a sturdy tree trunk or a pole just a few times, something magical happens. With each wrap, the friction between the rope and the pole adds up. The tension from the weight presses the rope against the pole, creating a normal force. This normal force in turn creates a friction force that resists the rope slipping. As you add more wraps, this effect multiplies on itself. A small holding force on your end of the rope can suddenly control a massive force on the other end. With just 2 or 3 wraps, a single person can easily hold back a weight that would normally take several people to control. This principle is not magic. It's pure physics, and it's a powerful demonstration of how friction can be used as a force multiplier. This superpower of friction is used in many real-world applications. Sailors still use this principle on modern ships with winches and cleats to secure heavy docking lines. When a ship is tied to a dock, the ropes are wrapped around large metal posts called bollards. The friction generated by these wraps ensures that the massive ship, weighing thousands of tons, can be held securely in place even when pushed by wind and currents. Rock climbers and mountaineers also depend on this effect for their safety. A device called a belay device, which the rope runs through, is essentially a specially designed mini capstan. When a climber falls, the belayer on the ground doesn't have to hold the climber's full weight. The rope running through the belay device creates a huge amount of friction, allowing the belayer to easily lock off the rope and catch the fall with minimal effort. This friction is the difference between a safe stop and a dangerous accident. So, the next time you see a rope wrapped around a post, remember the hidden superpower at work. It's a simple, elegant principle that allows us to control immense forces using the humble, everyday power of friction. It's one of the coolest and most useful applications of this invisible force. Friction is full of surprising and fascinating details. For instance, have you ever wondered why meteors or shooting stars light up when they enter Earth's atmosphere? It's not because they are on fire in the traditional sense. It's actually due to a combination of air compression and friction. As a meteoroid plummets toward Earth at incredible speeds, often faster than 25,000 miles per hour, it compresses the air in front of it. This rapid compression heats the air to thousands of degrees. This superheated air, along with the intense friction between the meteoroid's surface and the air molecules, causes the space rock and the surrounding air to glow brightly, creating the fiery streak we see in the night sky. Here's another cool fact. Spiders use a special kind of friction to walk up walls and even hang upside down. Their feet aren't sticky like glue. Instead, they are covered in thousands of microscopic hairs, and each of those hairs is split into hundreds of even tinier tips. These tiny tips create a massive surface area that allows the spider to take advantage of the same kind of intermolecular attraction we talked about earlier, the sticky part of friction. This force, called van der Waals force, is very weak on a large scale, but when you have millions of these tiny contact points, the combined frictional grip is strong enough to support the spider's weight against gravity. Did you know that earthquakes are also a story of friction? The Earth's crust is made of giant tectonic plates that are constantly, slowly moving. Where these plates meet at fault lines, they get stuck. The immense force of the moving plates builds up over years, decades, or even centuries, held in check by the massive static friction between the rocks. Eventually, the built-up stress becomes greater than the static friction, and the rocks suddenly slip, releasing a tremendous amount of energy in the form of seismic waves. That sudden slip is an earthquake. It's a dramatic, planet-sized example of overcoming static friction. Finally, think about the sound of a violin. That beautiful music is created by controlled friction. A violin bow is made of horsehair, which is coated with a sticky substance called rosin. The rosin increases the coefficient of friction between the bow and the violin string. As the bow is drawn across the string, it doesn't just slide smoothly. Instead, it follows a stick-slip motion. The bow grabs the string and pulls it, stick, and then the tension in the string becomes great enough to pull it back, causing it to slip and vibrate, slip. This happens hundreds of times per second, creating the vibrations that we hear as a musical note. The art of playing the violin is the art of controlling this stick-slip friction. So, what would the world actually be like if, in a snap, the force of friction completely disappeared? It would be instant, total chaos. The first thing you'd notice is that you couldn't stand up or walk. Your feet would slip out from under you, and you'd fall to the ground. But you wouldn't just lie there. You'd keep sliding in whatever direction you fell until you bumped into a wall. If you tried to grab onto something to stop yourself, your hands would slip right off. Nothing would have any grip. Anything that wasn't perfectly flat would start to slide. Cars, people, and animals on even the slightest slope would begin a slow, unstoppable slide to the lowest possible point. Getting dressed would be impossible. Your clothes would fall right off because the friction between the fibers is what holds them together, and on your body. Knots would come undone instantly. Shoelaces, rope knots, even the knot in a tie, all would unravel because there would be no friction to hold them tight. Screws and nails would pop out of the walls, and buildings and furniture held together by them would collapse into piles of wood and metal. Driving would be a nightmare. Pressing the gas would just spin the wheels uselessly, and pressing the brakes would do absolutely nothing. Cars would become uncontrollable metal boxes, sliding until they crashed. The very ground beneath our feet would start to change. Without friction to hold soil and rocks in place, erosion would happen at an incredible rate. The slightest wind or rain would cause massive landslides, and mountains would crumble away into flat plains. The world's landscape would be scoured smooth. Even the air would behave differently. The wind would blow at unimaginable speeds, as there would be no friction with the planet's surface to slow it down. The entire planet would become a loud, chaotic, and relentlessly moving place where nothing could ever stay still. In the end, a world without friction wouldn't just be inconvenient, it would be unlivable. It highlights just how fundamental this simple force is to the structure and function of everything around us. Friction is the force that provides stability, control, and order. It allows us to build, to move with purpose, and to stop. It's the silent partner in almost every action we take. So the next time you tie your shoes, stop your bike, or simply take a walk, take a moment to appreciate the invisible, essential force of friction. It may create some drag, but it's the grip that holds our world together. Science is all around us.